In this problem, we want to compute the sum of these Taylor series or Maclaurin series, to be precise. Okay. Here we're gonna start from 1, but when we have 1, we have 0. Okay, therefore we're gonna start from 2. Okay, and it doesn't matter, but starting from 2, okay, because we don't want to have terms that 0. So let's start from 2. Okay, so if we want to compute the radius of convergence, we're gonna find that it is infinity, and therefore the interval of convergence is the whole set R. Easy to prove using any of the methods that you know. Now we're gonna write it as a sum. Okay, so since this is a Taylor series, there is a function that corresponds to this one. Okay, using uniqueness and using what we know, because if we want to solve in general, we want to find the sums of the series, we have to solve differential equations. That's coming in the next few weeks. Okay, here we can start by simplifying this sum into two parts. So you have n over n factorial x to the power n minus the sum of x to the power n over n factorial. N is going from 2 to infinity. Okay, here we can simplify, and let's simplify first. We have n over n factorial, which is 1 over n minus 1 factorial x to the power n. Okay, I use the fact that n factorial is n times n minus 1 factorial, and I simplified by n. Here I can see that this is the expansion, the Maclaurin expansion of the exponential, but the first term corresponding to 0 and 1 are missing. Therefore, I add them to get the exponential, and I subtract them because I don't have them in the series. So this one give me this part here. Okay, note that the exponential, okay, start from 0. But here I have only 1, I'm starting from 2. Therefore, I'm missing 1 and 0. I add them to get the exponential, but I subtract them because they are not part of this series. Okay, so this is this part. Now I'm gonna focus on this part only. Here I can use, so here n is going from 2 to infinity. Okay, so first I'm gonna make this coefficient look like n minus 1. To do so, I'm gonna split this x into two parts, x to the power n into two parts. So I have 1 over n minus 1 factorial times x to the power n minus 1 times x. I will take this x outside here. Okay, so I'm simplifying and I'm telling all the steps. Forget about this one. I'm focusing only on this series, this Taylor series. Now I can use a change of index. So I'm gonna let n minus 1 equals k. Okay, so this one becomes, this series will become, I still have the x. So when n is 2, k is gonna be 1. When n is infinity, k is gonna be infinity. And I have x to the power n minus 1 is just k, and n minus 1 factorial is just k factorial. Now I see that they have almost the same thing, the exponential here, but I'm missing the first element. Therefore, I can add it and subtract it. So I have exponential, I added 1 to it, but I need to subtract that one. Therefore, I have this one now is equal to x exponential x minus 1 minus this second part, which is exponential x minus 1 minus x. Now I can simplify, get x exponential x minus exponential x plus 1 plus x. So I can simplify, okay? I can simplify all the elements that I don't need. The first one is this one here. It's gonna go with this one. And I can factor out, okay? I can get 1 plus x minus 1 e to the power x. Okay, and this is my sum for this series. Okay, if you want to check it, you can go back and work it out. But this is the sum of these Taylor expansion. Okay, so if we want to solve more general sums of this series, we will have to solve differential equations, the series that are solution to differential equations. We're going to see that later. But for now, the sum of this series is this one here. Thank you very much.